Today we're doing section 3.3, and this is our first application of the derivative. We're going to look at the most, really how this all started was looking at planetary motion and motion of objects and rates of change, velocity, acceleration, and you will learn that if you have a position equation, the derivative of the position is velocity. That's the rate, change in distance over change in time. That's the derivative of if you have an equation that describes your distance or your position at any point. And then acceleration is change in velocity over time. So that's the second derivative of the position equation. If position is distance, is telling you where you are at a given time, distance at a given time, then acceleration would be the second derivative. And there's actually a third derivative. Does anybody know what it is called? If you have your notes in front of you, you might see it, but it's jerk. You know, that's actually the change in acceleration over time, which is the third derivative. So the first derivative, if you have a position equation which tells you where you are at a given time, the first derivative is velocity, the second derivative is acceleration, and then the third derivative is jerk. And so we're just going to take a look at some of that today from physics. You may also remember that in physics, there was like vector and scalar quantities, okay, and do you guys remember speed is a scalar quantity, right? It was just like how fast you're going. It didn't matter in which direction. And the same can be true here. Like if you have negative velocity, what does that mean? Do you remember? Yeah, it means you're either going left or you're going down, right? And so the distance that you travel, you can have some overlap if you go left and then you go right, but your total distance may actually be further, more than if you just added your two velocities together over the time interval, or you added your position at the time intervals. So you kind of have to, we're going to have to consider that a little bit on these homeworks. Okay, so we will move now to the computer. And so the first question is, what is instantaneous rate of change, and what are some examples of its use? Oops, sorry. Okay, and so instantaneous rate of change it's hard to spell. It's got a lot of vowels in it to me. Rate of change is the derivative it's just the derivative. And so we have some examples. If you are given a position equation, so where you are at a given time t, velocity, the first derivative is velocity. The second derivative is acceleration. And then finally, your third derivative is jerk. Okay, so it's kind of the rates of change, the change in distance over change in velocity over, change in distance over time, change in velocity over time, and then change in acceleration over time. Okay, so we already sort of discussed modeling motion along a line, including displacement, velocity, speed, acceleration, and jerk, except that, yeah, okay? Yeah.
So the derivative of the derivative is acceleration.
If the question was, if you're given the position equation, the derivative of the derivative is acceleration. Yeah, it's the second derivative of the position. The first derivative, I mean, it kind of depends where you are. If you know velocity, the first derivative of velocity is acceleration. So, okay. Yeah. All right. And then I ask in the notes, it says to discuss modeling motion along a line, including displacement, velocity, speed, acceleration, and jerk. And so what we're going to be considering it is a particle that's just moving along a line, which is kind of feels weird because we're used to doing things in 3 dimensions or 2 dimensions, but we're just going to be on a line for now for simplicity's sake. So suppose that an object or particle is moving along a coordinate line. Is moving along a coordinate line. And so you just have a line, and then you have its position at time t, and then you may have its position at some change in t, t plus delta t. So you go some distance, delta t. So you just, like you could think of a little, like if, I'll do this in red, I don't know if you can really see it, but here's my object just kind of traveling along the line. And it may turn around, it can do all kinds of things. Well, not really, it's only on a line, so it's only on a line, so it's kind of limited. And so, if S of t describes the placement of the particle at time t, so the location at time t, then S of t plus delta t is just going to be where it's at. Delta t is the location, delta t later, right? Just obviously, like if you're at 1 second, and then if your delta t is 2 seconds, then the S of t plus delta t would be where you are at 3 seconds. Okay, and now we know that from physics classes or from past study that velocity is change in position or change in distance over change in time. And so you may remember the dirt equation, distance equals rate times time, right? And then you can actually solve for rate, which is your velocity. You can say that rate is equal to distance over time. And so here we're thinking of the change in distance over the change in time. So this is kind of old news that you've seen before. And so S of t then, we would call that position. S prime of t, we would call v of t, or velocity. S double prime of t is v prime of t, or a of t, which is acceleration, because it's the change in velocity over time. And then if we take the absolute value of the velocity, that is speed. So speed is a scalar quantity. It doesn't have direction. And then you also have S triple prime of t, which is a prime of t, or a v double prime. And this is what we call jerk. I guess you could call it J of t, although I've never seen it written that way. It's actually the first calculus book that I've ever even seen this jerk address. Other calculus books don't normally talk about it. Thomas is very much about, like, if you study his whole book, he wrote it for engineers at MIT, so he's very much about motion. So I think that's why he throws in a couple extra things. Okay. On the lecture notes, if you're following along on the lecture notes, I'm skipping number 3. It turns out to be not a very good example because some of the things I want to illustrate don't happen, and so I don't want it to. It's a decent problem, but it just doesn't illustrate what I want. So I'm going to move on to number 4, which does actually illustrate what I want to talk about. Okay, and so if you're looking at your lecture notes, we are told that on number 4, at time t, the position of a body moving along the s-axis It's weird, but it's like one dimension, the s-axis, all right? And the time is like, it's not even in 2 dimensions. It's just one. It's one. S is equal to t cubed minus 6t squared plus 9t. All right? And we're asked to find the body's acceleration at each time the velocity is 0. That's the first question. So part A, find the body's acceleration each time the velocity is 0. So find the body's acceleration each time the velocity is 0. Okay, so obviously you're going to need to find the velocity. We know s of t is equal to t cubed minus 6t squared plus 9t. Okay? And so how would we find the velocity? Well, we just learned that the velocity is the derivative of position. So we will just take the derivative of this function.
What's that M up there?
Oh, because that's in meters. That's where you are. You can think of the s-axis as like a meter, like on the meter stick, I guess. And that's a particular location. Yeah. Like it's really weird because you really only are in one dimension. You're just moving along the meter stick, and the time is sort of, at a given time you are at a certain position on the meter stick. You're not on a two-dimensional thing. Okay, so your velocity, v of t, is equal to s prime of t, which is going to be 3t squared minus 12t plus 9. Okay, did I go too fast, or are we good with derivatives? Hopefully you practice. The 3 comes in front, 3t squared to the 3 minus 1, which is 2. 2 times 6 is 12 to the 2 minus 1, which is t. And then the derivative of a linear function is just the slope, so it's just 9. Okay, so we want to figure out the acceleration when the velocity is 0, so we need to figure out where this equals 0. So we can, this is a quadratic, which we can solve by factoring. The first thing we might want to do is to factor out that 3 in front. And then you can divide by 3 without losing anything. And so you just have to solve for where t squared minus 4t plus 3 equals 0, which you can solve by factoring. This will be t minus 3 times t minus 1. So the velocity is 0 at t equals 3 and at t equals 1. Okay? Does that make sense? Yeah.
Does that mean like at the very beginning it's going at that speed?
Well, no, at time, no, this is where the velocity is 0. This is not when, at the time, at v of 0 is actually 9. What you're saying at the very beginning, what is the velocity? That would be putting 0 in for t. That would be 9. Does that make sense?
Yeah.
Okay. This is actually where the velocity if you think about it, what does velocity do? Well, velocity goes left and right, right? With what we're in our space, what we're talking about, since we're just on a line. So if the velocity is 0 at 3 seconds, what do you think is going to happen? What could happen? It could turn around. It may just stop. It may just like take a stop, you know, but it could turn around at that spot. Does that make sense? And at 1 second too. In order for the thing to turn around, it will have to have velocity for an instant to be 0. Do y'all agree with that? Okay, that's why it's important to know when the velocity is 0. We're not saying for sure that it's going to turn around, but if it turns around, it has to happen when the velocity is 0, just for an instant. Mm-hmm.
So could this be also like the vertex where the min and max?
It's sort of, except that we're just in. Yeah. But yeah, it would be, if you were thinking of a graph, it is where the horizontal tangent is. Yeah. Okay, so yeah, if you graph t cubed minus 6t squared plus 9t, that's a cubic function, and it has a max, or it may have a max or min. The only places they could occur are at 3 and 1. Okay, now we were just but staying with the question, which was find the body's acceleration each time the velocity is 0. So first we found where the velocity equals 0. Now we just need to find the acceleration equation, which is what? The derivative of velocity. And so here's our velocity, so it's going to be 6t minus 12. Are y'all good with that? All right, and so now to answer the question, which was what is the body's acceleration each time the velocity is 0, we'll figure out what a of 3 is, which is 6 times 3 minus 12, or 18 minus 12, or 6. And we are talking per second, so this is meters per second squared, and these are both seconds. And then a of 1 is 6 times 1 minus 12, which is 6 minus 12, or negative 6 meters per second squared. So those are our accelerations. Then we're asked to find the body's speed each time the acceleration is 0. Okay, so this is a different question now. So now we're going to figure out when the acceleration equals 0, and then we're going to take that time and we're going to plug it into our velocity equation, but we want to take the absolute value of the velocity because speed is not positive or negative. Does that make sense? So that's this question. Find the body's speed each time the acceleration is 0. Okay, so our acceleration equation was 6t minus 12. We're going to set that equal to 0. And we get 6t equals 12, or t equals 2 seconds. So when the acceleration is 0, our speed, which is equal to the absolute value of v of t, or the absolute value of v of 2, and so the absolute value of v of 2 is equal to the absolute value, our v was 3t squared minus 12t plus 9. So 3 times 2 squared minus 12 times 2 plus 9, or this is going to be 12 minus 24 plus 9. And that's negative 3, but we take the absolute value, so 3 meters per second. All right, and so when the acceleration is 0, your velocity is going to be at either a maximum or in this case, your speed is going to be at a maximum. Your velocity could be negative, but it would be the most negative that it is. Does that make sense to you? So if you just think about it this way, if you have the velocity here is a quadratic function, right? It's going to have a max or a min, right? If we look at this quadratic function that we have 3t squared minus 12t plus 9, it actually has a what? Oops. It actually has a min, right? But if you think about it, that vertex where it's horizontal, that's going to be the it's going I always get this. I'm sorry. It's going to be a max or a min, and so that minimum, the derivative of this, where it occurs at 2 seconds, if you plug that 2 in, that's going to be and when you take the absolute value, that is going to be the maximum speed that the particle reaches. It's hard because you want to mix up your graphs. I'm sorry. Okay, so now let me see if I can clean this up with part C. Find the total distance traveled by the body. The total distance traveled by the body from t equals 0 to t equals 2. All right. Now, S of t is equal to t cubed minus 6t squared plus 9t. And what you need to do is, what you might want, what we already talked about is we knew that, we know that the velocity equals 0 at t equals, what was it, t equals 1 and t equals 3 seconds. So the 3 seconds isn't worried because we're just looking for total distance travel between 0 and 2. But we need to be careful. We can't just look at where we are at 0 and where we are at 2 and say that's the total distance traveled. Okay? Because in that interval from 0 to 2, the velocity becomes 0. And so there is a chance that this particle turned around. And if it did turn around, then it would have gone some distance to the right and then some distance to the left. So the total distance traveled would be more than just the distance at 0 to 2. Does that make sense? If you just looked at where you are at 0 and where you are at 2. Okay.
If you driving somewhere and then you forgot something.
And you go back. Yeah, that's what you have to realize that. But it may only look like you only went from start to finish, but in truth you turned around and then went back. Okay. So you might be able to see that if you consider some points. All right. So let's think about S of 0. S of 0, well, we start at 0, right? What is S at 0.5? Well, that's going to be 0.5 cubed minus 6 times 0.5 squared plus 9 times 0.5. All right, I did this before, I got 3.15. Let's make sure that's correct. So 0.5 cubed plus, or minus 6 times 0.5 squared plus 9 times 0.5, which is 3.125. Okay, so then you're at 3.125. And then at S of 1, if you plug 1 in, you're at 1 cubed minus 6 times 1 squared plus 9 times 1. Now you're at 4. Right? Does that sound right? 1 minus 6 is negative 5 plus 9 is 4. Okay, so that seems good. It seems like you're just moving along from 0 to 3.125 to 4, okay, on the meter stick, no problem. All right, let's try 1.5. 1.5 cubed minus 6 times 1.5 squared plus 9 times 1.5. So we got 1.5 cubed minus 6 times 1.5 squared plus 9 times 1.5. Oh, now we're at 3.375. Okay, so that means we must have turned around. Does that make sense to y'all? Between 1 and 1.5, somewhere we turned around. Okay, because now we're back at 3.75. And then at S of 2, if you type that in, I promise it's 2. So we're going back left. Right, so if you visualize this on your meter stick, yeah.
So all we need to know is this is between 0 and 2. If it passes 0 and then comes back, do we also
Well, the time is 0. If it passes 0, meaning, the meter stick starts at 0.
Yeah, like from the beginning, the question was from the beginning all the way to 2 seconds, right?
Right, yeah.
And then, but and you were saying the distance in between that. Okay, but that's what I was asking. If past 3 seconds, it wouldn't matter. So.
Well, in this particular, it's interesting because we do know that the velocity changes at 3 also. From the first problem, it changed the velocity was 0 at 1 second and at 3 seconds. So something may be happening. If I had asked you on the interval from 0 to 4, we would need to see what happened at 3. Yeah, but it's just not in this case. We only wanted from 0 to 2, so we don't need to worry about 3.
Would there be an easier equation than just 8.5 of each one?
I only even did this just to kind of illustrate that it did turn back around. What you would do normally is not this. I'm just trying to get you to see what's happening. Okay, so if this is your meter stick, and you've got it 0 and then 1 and then 2 and then 3 and then 4 and I don't know, whatever. Well, I guess it's not a meter stick. It's just a meter thing because a meter stick only has 3 meters on it, right? Okay, and then you have to think of the particle, and I'm going to put it up top just to kind of show you. But he's traveling along. At 0, he's at 0. And then at 0.5, he's at 3.125. So he must have gone this way. On top of the thing. And then at 1, he's at 4. But then at and then at 1.5 seconds, he's at 3.375. So he comes back and he does something like this. So he comes back, and then at 2, he's here at 2. You see what I'm saying? So he takes it, and so this is weird because this is not time, this is meters. So this is t equals 0. Here's t equals 1. Here's, t equals 0.5. Here's t equals 1, and then here's t equals 1.5, and then here's t equals 2. So that's there is some backtracking. And we know that he doesn't actually go any further. He has to turn back around. How do we know he has to turn back around? Well, we can figure that out by looking at the velocity, the change, how the velocity, whether it changes from positive to negative. So let's say that. We found where the velocity equals 0, and we must investigate the velocity on either side, and it's not really, this should be, we found when. We must investigate the velocity on either side of this time to see if it changed direction at that point. Now, we know it did because we looked at some points and we know that it did. But say you weren't plotting these points, like you're saying. Say you didn't arbitrarily pick points. Let's see how we could do that to see if there is a change in direction. At that point. Okay, and so all you have to do is look at your velocity equation on a number line. Now this now is going to be time. T. This is time. Or down here is going to be time. And we know something happened at 1 second. All right? And so I want to consider the velocity to the left and the right of 1 second. So our velocity equation was 3t squared minus 12t plus 9. I know when I plug 1 in here, I get 0, right? If I put 1 in, I get 0. Obviously, v of 1 is equal to 0. So I want to pick a value to the left of 1, like 0.5. v of 0.5 is 3 times 0.5 squared minus 12 times 0.5 plus 9. And if you type that into your calculator, you should get 3.75. Okay? So, and this is from 0, on the interval from 0 to 2 seconds. So I could have chosen any number from 0 to 1, and I will get a positive velocity value. I'll get a positive number. And what that means, since it's positive, it means that it's going to the right. Oh, are y'all leaving?
Yeah.
I thought you didn't have to go.
No, we don't have a February today, so we get it at 38.
Oh, all right. Okay. So S of t is going to the right. You can pick this up on the video then. I'll see you guys later. All right. Now, if I pick a value to the left or to the right of 1, like 1.5, if you type that into your calculator, you get negative 0.225, or just negative 0.25. This means S of t is going left. So when you have negative velocity, it means the speed is 2.25, but the direction is to the left in this application because we're looking at a particle on a number line. So this means left, going left, and this means going right. And at 1 second, it changed direction.
Question.
Yeah.
So when the velocity equals 0, that's where the highest speed will be, correct?
When the velocity equals 0, is that the highest speed? No, because that would be when the velocity equals 0, the speed is 0.
Okay.
So that it is a good question though. So where does the maximum speed occur? That's your question? And that would be when the acceleration equals 0.
Okay.
That's why we asked when the because when the acceleration equals 0 is you're going to maximize your velocity. Does that make sense? So that's why we asked it. Okay. So when we look at, the question was that we need to figure out what the total distance traveled was. So we actually need to look at 2 intervals. We need to look at the interval from 0 to 1, and then the interval from 1 to 2, and find those total distance traveled. Does that make sense? Because there's a split there. So we have to figure out from here to here, and you can see it on the picture. You can kind of automatically determine what the distance traveled is, because we see from 0 to 1 second, it went from 0 to 4, right? And then from 1 until 2, it went from 4 to 2, so it traveled 2 meters. So the total distance traveled is how much?
6.
There you go. Are y'all with me? It goes from 0 to 4, and then it goes from 4 back to 2, so the total difference is 6. The problem, the whole reason I had to do this is if I had just looked at S of 0, which is 0, and S of 2, which is 2, I would have told you that it traveled 2 units, and that's not right, is it? It actually went all the way to 4 and then back to 2, so it traveled a total of 6 meters. Okay, so we couldn't answer this question without looking at the velocity and seeing if it ever changed over the interval that we wanted. And then we had to investigate, okay, if the velocity does equal 0, did it just stop there, or does it go back and forth? Does it, go left and then right? Because it could be that it just stops for a second and then it starts back up again. So that wouldn't have mattered. Okay? All right. So to find
Is there one where like it slows down?
the total, well, this one slowed down and sped back up, right? I think. Let's see. Did we ever? Yeah, because it slows down. We didn't really look at the velocity, but this is you could pick some other times, or you could consider this is a parabola that. Okay, this is a parabola that goes like this, right? And so over the interval from 0, it was from 0 to 2 seconds. So when we were at 0, we were at 9. And then at 1 second is when the velocity is 0. And then, okay. So, yeah, it is slowing down until it gets to this point right here at 1 second, and then it does speed back up. So it is, because it's a parabola, it's, is that right? I'm just really getting myself confused, because it does seem like over this interval, its fastest time will be at 2 seconds. What is v at 2? 12 minus 24 plus 9. We did that already, didn't we? Up here, did we find? Yeah, we did show that at 2 seconds, it was 3 meters per second. V of 2 was 3 meters per second. I really am going to have to do just every semester. I get a little better at this section, but I need to do just a little bit more work there. I see what you're asking. I'm not doing a good job explaining it, though. I mean, yeah. Can you help me out, Daryl?
Oh, no.
No.
I just had a question about part C.
Okay. You ready to answer C? Okay. So to find the total distance traveled, is that part C?
Yeah.
Okay.
In one of my physics classes, when
Yeah.
you're taking total distance,
Yeah.
you just counted its change from initial position to where its final position is. And if it backtracks, you don't count what was, like, how it changed direction?
Yeah. Uh-huh.
In physics, we just count that distance from initial point to its last point. And
Why? Really?
yeah, you don't take into account, like,
Even if it said, what is the total distance traveled?
yeah, I think that's how we did.
I can't imagine that. I mean, it must have been asking something else. I mean, the wording must have been something else, and it must have kind of messed you up. But if it's asking for total distance traveled, what you're saying maybe would have been, what would that be?
Total distance between the points.
Or something, or, yeah, because, total distance traveled absolutely is going to, that's the whole reason we're doing this, is that we have that velocity.
Confused because our
Yeah, I'd have to see that problem. I'd like to see it, and compare it to this one, because I'm sure there's just slightly different wording where you throw out and not worry about what it does in the middle.
just kind of getting hung up.
Yeah, I would think, because it definitely matters in this example. So, okay, so this is the total distance traveled. You need to consider on the interval, consider the intervals from 0 to 1, and then from 1 to 2. Okay? And so you are going to do the absolute value of position, this length, the length of this interval, which is S1 minus S sub 0, plus the absolute value of the length of the second interval, which is S sub 2 minus S sub 1. Okay? And so S sub 1 minus S sub 0, that was when we went at S sub 1, we were at 4 second, we were at 4, and S sub 0, we were at 0. And then at S sub 2, we were where were we at S sub 2? We were at 2. And at S sub 1, we were at 4. And so in absolute value, you do get, this is 6 meters traveled. Okay. And I know I didn't do a good job. I'm going to work on that acceleration question for you to do a better job. I'm sorry. But I need to move on. Is that okay? Yeah. Okay. I know. I'm upset with myself, though. All right. Now, on number, pardon?
Curious.
Yeah, it's a good one. I just need it. The next question is, what did Galileo learn from his experiments with free fall? And Galileo is really pretty cool because he didn't have like an infrared camera or really anything to figure out what this rate of change was, what this pull of gravity is, that we can sort of observe. We have all these special tools that we can actually see the gravitational pull. He just did it through observation. And if you ever read about Galileo, and this is true of Newton too, these are men that their whole lives they spent thinking. All they ever did was think and observe and think and observe and think and observe to the point where they would be outside looking at something, thinking about its motion, and they could see what a normal person couldn't see. I mean, they really could. And then they made these conjectures that were later proven to be true. But it was like they thought and watched and observed the world around them, the physical world around them so much that they were able to see what other people couldn't see. And I don't know if that's happened to you yet in your, I don't know what it is that you obsess about, but when you start to obsess about something enough, you really do get insight. So I hope that you do find something that you, I mean, obviously not a person or something, because then they make weird movies. But, I mean, I hope that you find something that really interests you and you really let your mind feel it, because it's unbelievable what can happen, you know, how you can achieve and what you can discover. And it kind of feels good when you see something right away, I mean, not to be snooty, but and other people are like, what? And what you're saying is right, you know. So do that in something. I mean, I'm sure there's something that you do. Do something really well. Galileo was really good at observing the universe, and so was Newton. So, I mean, who knows what your thing will be, but it's kind of neat. So anyway, he found that he discovered through observation that this is the equation that will model the height at any given time if it's just free fall. Like if you just drop an object from a certain amount of time, this equation will model its position. And the G, of course, is the gravitational constant, which he had an approximation to. And now it was all sort of in his units and that sort of thing, but it's just kind of cool. So he gave us this equation, which you plug in your G. What are familiar G's? Do you guys have, it's your gravitational constant.
8 meters per second.
9.8 meters per second squared is a good one. And what's the other one?
32 feet per second.
There you go. So where S is the position or distance fallen or distance dropped at time t. And G is the gravitational constant. And G equals 32 feet per second squared, or 9.8 meters per second squared. And in Cal 3, in this textbook, we actually derive this equation. We prove it. It gets proved to you. I don't know if you'll have me, but if you do, I'll prove it to you. But it's kind of a downer, because by then you've almost already had physics. You probably had the second course in calculus-based physics, and you've already seen the derivation. So, and you've also seen this equation a million times in a you know, that 1/2, or you've probably seen negative 16 t squared plus v naught t plus h naught, you've probably seen that equation, right? Have y'all seen this one? S of t equals negative 16 t squared plus v naught t plus s naught. And this is, or h, sometimes they call this h naught. S naught is okay. But, and so this is the position, it is a distance dropped at a particular time t. And it's just, just the distance dropped. But if you want to then put it around something that makes more sense, you may want to drop it from a particular height. So that's what the h naught is. And then this v naught t is maybe you want to like throw it or launch it or, and so it becomes a more exciting equation. But this part right here is from this right here. Because if you have, and actually a lot of times this is negative 9.8 meters per second squared and negative 32 because it's a pull in the downward direction. Okay? Does that make sense? Okay. And, if you're, this is of course on the Earth at sea level. If you're in a different planet or a different location, like on a mountain, it has different things going on. So, for example, we have some Freefall Equations. This is number 6. Like Mars and Jupiter are slightly different. The Freefall Equations in meters per second on Mars and Jupiter. This is in. Are, let's see, so for Mars, we get, let's see. Mars is S equals 11.44 t squared. You're heavier on Mars, I guess. And in Jupiter, Jupiter's where you go if you want to weigh less, is that right? Jupiter is 1.86 t squared. Okay, and so we have a question then on each of these planets. How long does it take a rock falling from rest to reach a velocity of 27.8 meters per second on each planet? How long does it take a rock falling from rest to reach a velocity of 27.8 meters per second on each planet? Okay, well, velocity is the derivative of position. So on Mars here's our position equation. So our velocity is just the derivative of that will be the velocity. And so that will be what? 22.88 t. And then the question is, how long will it take? So all we have to do is set this equal to 27.8 meters per second and solve for t. And we get t equals 1.219 seconds. That's on Jupiter. Or, wait, is Jupiter's? That's on Mars. Did I copy that right from the notes? Let's see. Oh no, I have it. Darn it. I haven't messed up. This is what I get. I know.
Mars was smaller, but
This is what I get for not having this typed. This one's Jupiter.
okay, that makes sense.
I can't read. I can't read my own notes. And this one's Mars. Mars is, 1.86 on Mars and 11.4. Okay, so this is Jupiter. Sorry. Oh, geez. All right, so Jupiter, we got 1.219. I have no excuse. I need to pull it together. All right, now Mars, we have S equals 1.86 t squared, and S prime is equal to V, 1.86 times the derivative of, so now the derivative 1.86 times 2 is 3.72 t, and we just set that equal to 27.8, divide by 3.72, and we get, it takes a little longer on Mars, doesn't it? 7.47 seconds. So I guess you're heavier, that's right, you're heavier on Jupiter, right? I think I heard that. But on Mars, you weigh less. So if you live on Mars, you'll feel better about yourself.
Actually, you'd be fatter.
Will you be fatter?
Yeah, you look like you'd eat more. So
Yeah, you'd be fatter, but you wouldn't weigh as much, so you would feel good. But see, if you were born on Mars, you wouldn't have the same perspective of your weight as if you traveled to Mars. So you need to live a big portion of your life to really benefit feeling skinny or something. I don't know. Okay. Let's look at number 7.
The goal is to live on Jupiter and then go to Mars. How faster you would be.
Yeah, live on Jupiter and then go to Mars. Yeah, you'd be really... Yeah, well, like even in Mars, like if I went to Mars, I would be a really fast runner, even faster. Yeah.
If you could stay on the ground.
Yeah.
Because you'd be like a lot of running is actually use your muscle push off.
Oh, right. Yeah. It may not work out for me. Maybe I'd be a really good hopper. Okay. Number 7. A rock thrown vertically upward. A rock thrown vertically upward from the surface of the moon Oh, it won't even erase. At a velocity of 24 meters per second, reaches a height of S equals 24t, that's where your velocity comes in, minus 0.8 t squared. This is my Galileo's Freefall equation, but taking into account the moon's gravitational pull. Yeah, meters in t seconds. Or, well, you should understand the units from the 24 meters per second. Okay, so now we'll have some, these are kind of classic questions that we get to answer. First, you're asked to find the rock's velocity and acceleration at time t. Find the rock's velocity and acceleration at time t. That's easy enough. S of t is this, 24t minus 0.8 t squared. So v of t is just the derivative, which we learned will be 24 minus 1.6 t. And a of t will be the derivative of velocity, which is what? And so what do you think that negative 1.6 is? Well, that's acceleration. It's actually the gravitational constant on the moon, right? Okay. Now, B asks, how long does it take to reach its highest point? And you could actually, because our equation is quadratic, you could take all the calculus fun away and do this with a college algebra question, which is basically you you can find it's going to be at the max, right? So negative b over 2, which is the vertex, negative b over 2a. But it's kind of fun to recognize that you could use calculus to do this, because when it reaches its max, it's going to go up and then it's going to come back down, and so the velocity is going to be 0 at that point, right? So it's fun also to recognize that this will occur when v of t is equal to 0. Because that's when that change will occur. And so then that'll be t equals 24 over 1.6, which is if you type that into your calculator, you get 15 seconds. So it goes up and it comes back down. Now, you could also have found the x-coordinate of the vertex, negative b over 2a, which would be negative 24 over 2 times 18. I mean, you can see it right there, right? It's kind of interesting. Okay, how high does the rock go? Okay, well, take this maximum height, this time when the maximum occurs, and plug it into the original equation. So S of 15 is equal to 24 times 15 minus 0.8 times 15 squared, which is then, if you type that into your calculator, 180 meters. Again, you could have done with algebra, but it's not as fun. Okay, how long does it take the rock to reach half its maximum height? All right, let's see. How long to reach half its maximum height? Well, that's just kind of a silly, half the max is what? Half of 180 is equal to 90 meters. And where are you going to plug that 90 meters in?
Would you set that to either the velocity, or would you set the main equation to equal 90?
Which equation will you set equal to 90? Yeah, you have to, the position equation, because this particular question doesn't have anything to do with the velocity. So yeah, you're going to put this into the position equation. So you're going to have 24t minus 0.8 t squared equals 90. And then you can solve this a variety of ways. I'm going to put it in order. Negative 0.8 t squared plus 24t minus 90 equals 0. And so how will we solve that? Okay. And then what? Yeah, that'll work. But it's still probably going to end up having to use the what? Quadratic formula. Yeah, we can factor the 0.8 out, and they'll make our numbers smaller. Although, does 0.8 go into 90? It may just make a mess. But I think you're going to need to use a quadratic. I was looking for a quadratic formula. So do we remember it?
X equals negative b plus or minus square root.
B squared minus 4ac all over 2a. Okay, we got it. All right, and so our A is negative 0.8, our B is 24, our C is negative 90. And so we get negative 24 plus or minus the square root of 24 squared minus 4 times negative 0.8 times negative 90 all over 2 times negative 0.8. If you type this into your calculator, make sure you put your denominator in parentheses. Anyway, you can type that in, and you get you actually get 2 answers, but 4.39 seconds, and then you get 25.6 seconds. But the question was, how long does it take to reach its maximum height? So, or half its height, so it probably wants it on the way up. Because it's going to go on the way up, it'll be at 90, and then when it comes back down, it'll be at 90. So it happens, at first time it happens at 4.39 seconds, which is probably what they're asking for. Then it says, how long is the rock aloft? This question never goes away. you'll find, have you found these on your online homework? It has like 10 parts remaining, you'll say, or in the bottom, you know. Did y'all notice that or no?
Yeah.
How long is the rock aloft? How would you figure out that?
Is that where you'd find the total distance, the absolute value of?
Well, that would be, we actually want to know time. We want to know the time. So what is the time when it starts? Or no, sorry. What is the height when it starts? 0. And what is the height when it ends? So if we could figure out where the height, the position equals 0, it'll tell us when that occurs, which is answering the question, how long. Okay, so the height, the position is 0, the height, or position equals 0 when it hits the ground. Hits the ground. So this is still just an algebra question. We just have to take that position equation, 24t minus 0.8t squared, and set it equal to 0. Which this one we can do with some quick factoring. I'm just going to take t out. So I get 24 minus 0.8t equals 0. And so obviously t equals 0 is a solution. But the other solution is t equals 30 seconds. It's a long time. Are we on the moon or something?
Yes.
Yeah. Okay. All right, so there. That question only had a few calculus questions in it. I remember when I was studying that we would do these forever. We did these types of questions, these position equations. Do y'all remember those? Yeah? Do you get them a lot now in physics? Or is it just one unit?
It's usually just one unit, and then move on to like rotary motion.
Oh, okay. All right, we're doing good. We're at 10:06. I got a few more questions. Let me at least get to number 8, and then, okay. It says the figure below shows the velocity v of a body moving along a coordinate line. Okay, so this is where you really kind of have to think about, I like these problems because they make you think. All right, we're going to count by 2s to 10. So this is 2, 4, 6, 8, 10. And this is time in seconds. And then we're going to go from 0 to 3. This is 3. All right, and so this is -3. All right, so it looks like, I'll just place the places where we cross between 6 and 7. And then at 8 we get up here. And then at 10 we're back here. And then, okay. So it goes up like this, and then it goes down like this, and then it's like this until about 6, when it goes like this. These are straight lines. Okay, so that's what you're looking at. And this is the velocity. In meters per second. Okay, and so this is the velocity of a body moving along a coordinate line. All right, so now we have to answer some questions. I really like these questions. They're testy type questions. When does the body reverse direction? Good. At 2 and at 7 seconds, right? Because it changes from positive to negative, and the velocity is 0 at that point. It has to do both. It has to change also. I mean, it has to go from positive to negative. So if it just kissed the axis, like at 4, if it just was stayed negative but just kissed, that means that it just stopped for a second, but it didn't change direction. Does that make sense? But since it actually passed through the axis, that means here the velocity is positive, it's going right, then all of a sudden the velocity is going left. I mean, the velocity is negative, so it's going left, so it must have changed direction at 2, the moment that the velocity was 0. Okay, so this is at t equals 2 and at t equals 7, because this is where velocity equals 0 and changes sign. Okay? Now, when approximately is the body moving at a constant speed? Yeah. That's just when you're horizontal. Right? Speed. So that would be from about 3 to 6. All right, C. Graph the speed for, on the interval from 0 to 10. Okay, so graph the speed on interval from 0 to 10. All right, I'm just going to do it in red. The only thing that's different about speed is that it's never negative, right? So you're going to have, these negative parts are going to come up. And so it's going to go like this, and then like that, and then like that. And it's also going to be on this part too. Does that make sense? Yes, that's speed. Is the red graph. And then you're asked to graph the acceleration where defined. Okay, so that's part. So this is in red. On graph. Okay, and so we kind of did one like this last time, or maybe last week sometime. Graph acceleration. What do we know about the acceleration?
Changing velocity over time.
Right, and it's the derivative of the velocity. And fortunately, our velocity is linear all along, right? So all we have to do is figure out the slopes over these little intervals, and then we can draw the acceleration will just be little horizontal lines representing those intervals, right? So do you see that from 0 to 1 second, the slope is equal to, would that be 6? Because it's up, no, it's 3. Up 3 over 1, right? So slope is 3. And then from 1 second to 3 seconds, the slope is, I think it's -3, right? Because it goes over, it's -6 is the change, but it's 2 spaces. So that's -3. Okay, and then from 3 seconds to 7 seconds, the slope is 0. And then to 6 seconds. And then from 6 seconds to, is that 8 seconds? We would say that the slope looks like +3. And then from 8 to 10, it's actually 1.5, I would say, because -1.5, because it's actually a little steeper. Over this 2, it goes to 3, so it's 3 halves. Changing y over changing x is 3 over 2, -3 over 2. Okay, and these are your acceleration. So if you were going to graph acceleration, you're from 0 to 1. Let's see. 1, 2, 3, 4, 5. Or maybe we better count by tens. 2, 4, 6, 8, 10. From 0 to 1, you're at 3. So you kind of open circle, boom, open circle. And then you don't want to get to all the way to 2. And then from 1 to 3, you're at negative 3. So from 1 to 3. And then from 3 to 6, you're at 0. Maybe I'll do these in a different color. So from 3 to 6, you're at 0. And then from 6 to 8, you're at 3. And then from 8 to 10, you're at negative 1.5. And you do have open circles on the endpoints because you have corners there, so the derivative's not defined. This is acceleration. It's kind of fun to think about the graphs of these and how they're related. You think? I don't know. It kind of hurts your brain a little bit. But I think it really puts it in perspective. You're not just doing all the equations, but when you look at the graphs, you're really kind of starting. Okay, I did not get to number 10, but it is in the other lecture room. I don't know if I want to keep y'all. I hate to make y'all stay again. So do not stay unless you want to. You're not going to hurt my feelings in any way. I will complete the lecture because I have people, maybe somebody is watching this. I can't imagine they're not bored out of their mind. But wait, let me just show you my picture of people before you leave because it's kind of fun. You don't have to stay for 2 seconds. But okay. So it's in summation, if you're talking about rate of change of anything, you should take a derivative. They're oh so useful. And so then our little guys, good idea, Newton, and then he says, thanks, Galileo. And so there's Newton and Galileo, and then here's me. Being funny. Okay. All right. I actually got in the paper. I was in the paper for that. You know, if you act ridiculous enough, you can get your picture in the paper. All right, so. Okay, I'm going to finish this, but you will not hurt my feelings if you leave. We're just going to, it's boring anyway because it's like how to use math to make money, and that's not fun. But anyway, we're going to do some one business application. So what is the vocabulary used by economists to describe rates of change? And then those words are marginal cost and marginal revenue. If you've ever taken a business like class, you may have heard those words or an economics class even. Those words are marginal. Have y'all heard those words before? Yes? No? Rates of change in economics. In economics are called marginals. So you have marginal cost and marginal revenue. So the last question, number 10, suppose that the dollar cost of producing X appliances is, suppose the dollar cost to produce X appliances is, all right, C of X is equal to 1,400 plus 130X minus 0.3X squared. So this is our cost function. The average cost per appliance of producing the first 150, find the average cost per appliance of producing the first 150 appliances. Okay, the average cost. All right, so your interval is from 0 to 150. And remember, average rate of change, you just do change in y over change in x over the interval. So you're going to do the cost. Remember, it was f of b minus f of a over b minus a. Well, here it's going to be c of b minus c of a over b minus a, where b and a are your 0, or b is 150 and a is 0. So the cost of 150 minus the cost of 0 over 150 minus 0. So if you type that into your calculator, you'll get the cost at 150 is 14,150, and the cost for 0, I guess there's some fixed costs, maybe to hire the people or something, and so that's $1,400. So on average, it's $85 per appliance for the first 150 appliances. So then it says find the marginal cost when 150 appliances are produced. That's this new thing. Find the marginal cost when 150 appliances are produced. Okay, so we want to find c prime of x. So that's your derivative. C of x was given to be 1,400 plus 130x minus 0.3x squared. So c prime of x is going to be 130 minus 0.6x. So if you put 150 in there, it's 130 minus 0.6 times 150, which is $40. It's the marginal cost. And what the marginal cost is, okay, let's see. What in economics, what it means is it's about what it would cost to produce the next appliance. So the cost that it would be to produce the 151st appliance. That's what they mean. So the next question is show that the marginal cost when 150 appliances are produced is approximately the cost of producing one more appliance after the first 150 have been made by calculating the latter cost directly. So if I calculate what it would cost to produce 151 appliances, we know 150 appliances, the plain old cost of 150 appliances was that 14,150. If I were to calculate the cost to produce 151 appliances, just plug it into the equation, I get 14,189.7. This difference is $39.70, right? C of 151 minus C of 150 is equal to $39.70. Which is pretty darn close to what the marginal cost is, $40. Okay, so we think of the marginal cost is the amount to produce one more over a certain interval or something. So if you went from, what would the cost be? So I don't know. They use that because then they want to minimize it to figure out, what production level would minimize cost. Because you can imagine it doesn't, you save money for a while, but then it starts to cost more, to produce as you're producing, it costs, there's a particular point when you're producing and you have minimized the cost, I guess, because you're at full capacity. And you're producing and whereas if you produced any more, it would cost more because you have to buy a bigger building or have hire people working longer or whatever. Okay, so that's it. We finished. Ugh.